Gresham College is honoured to welcome Alain Goriely as its new Professor of Geometry, and I hope you'll join me in welcoming him to the stage to deliver his inaugural lecture, which has, for him, the appropriate title of The Big Brain, Size and Intelligence. Ladies and gentlemen, Alain Goriely.
Thank you. So for my first years as Gresham Professor of Geometry, I will be looking at the intimate relationship between mathematics and the brain. Now, the brain, as we know, is the seat of feelings, senses, and of course, all mathematical thinking. But when we look at a sagittal slice, like the one you see, as a mathematician, you see a lot of structure. You see complicated geometry. You see a network of filaments connecting different parts of the brain. You see dynamics, brain talking, different parts talking to each other. It's therefore a natural question to see how this geometry, architecture, topology, network, all impact brain function. And we will be looking at this question in quite detail in the next few lectures. But today, to start, I will start with a seemingly simpler question, which is how the sheer size of the brain is related to its performance, let's say intelligence, both among us, humans, but also comparing ourselves to animals. So since we will be talking about mathematics and the brain this year, the best way to start is, of course, the brain of a mathematician. But not any mathematician, maybe one of the greatest mathematicians of all time, Carl Friedrich Gauss. Gauss was born in 1777 at Brunswick. He was, of course, a child prodigy and moved quickly to Göttingen, where he spent his entire life. As a teenager, he got interested in a classic problem that goes back to Euclid, 300 BC, which is the problem of constructibility, which is how to draw an n-sided polygon with just a compass and a straight edge. No progress had been made until Gauss came 2,000 years later and showed that the 17-sided decagon, the heptadecagon, could be built with a compass and a straight edge. Its construction is not step by step, or you do this circle and all that, but he actually relies on a relationship between trigonometry and algebra. He showed that if you can write the cosine of 2 pi over 17 purely in terms of square root, like in this formula, then automatically it will become constructible. Of course, he didn't stop there, but this particular problem shook the entire mathematical world at the time and made him decide to go into mathematics rather than philology. During his PhD, he proved the fundamental theorem of algebra, and he went on through his entire life. He revolutionized number theory, algebra analysis, but he also had seminal work in physics, where his work in electromagnetism, such as Gauss's law, remains fundamental to this day. He was the director of the observatory. He made great contribution in astronomy and geodesy, or to measure the world. He built the first heliotrope, which is a way to measure distance. He built the first electromagnetic telegraph in Göttingen, and also, as we will see, in statistics. But all good things come to an end. And on 23rd of February 1855, Gauss died in his house of a heart attack. He was so well known at the time that the King of Hanover had commissioned a special medal honoring his death and his life, where you can see at the bottom Mathematicorum Principi, which is often mistranslated as the prince of mathematics, but could be better translated as the principal of the foremost, or as kids would say, he was the goat of mathematics. What was a great loss for mathematics and science was a great opportunity for one of his colleagues, Rudolf Wagner, who is an anatomist from Göttingen. around 1855, anatomy, and especially the study of the brain, was in a bit of a crisis. And what was the problem? Well, let me take you back about 50 years before with the debacle of phrenology. Phrenology was based on two basic ideas, that the brain is divided in different modules that correspond to different types of function, poetry, wit, number, and so on, and that when the skull is formed, this ossification would be a marker for all these modules. So that if you have a burn in a particular region of the brain, that means that your brain is bigger there and that you are somewhat better at that particular skill. And Gall, Francis Joseph Gall, was one of the promoters of this theory. And for instance, if you're good at mathematics, then these two regions in your forehead would be bigger. And don't look at me like that. And they went on around the world. It was very popular. They went at salon and they were palpating skulls and telling people how great they were, just like modern astrology or something like that. Here is a cartoon depicting them, up to the point they went to Paris. And Francis Gall came to Paris, and there was Napoleon. And we know that it doesn't take a genius to leave Europe, but to conquer Europe is an entirely different matter. And Napoleon was no fool. He was trained as a mathematician, as a scientist, and he was very suspicious of phrenology. So he asked the French Academy of Science to look into the matter, and they produced a quite big report saying that there was nothing to it, that it was complete pseudoscience. There was no relationship between the two. So at least on the scientific side, the theory of phrenology was completely discarded. But it was so popular that it stayed for at least a century, and to this day, we still have the effect of it in some sense. We still describe people, low brow, and so on, big brain. So all these are still the remnants of phrenology. But at the time, there was also another idea. How do you solve this problem? And that's the idea was first proposed by Georg Christoph Lichtenberg, who was the physics professor of Gauss at Göttingen. And his idea was to study the brain. And he said, what ought to study in every nation the greatest man, the prison and the asylum, since these three categories are the three primary colors of which the mixing produce all others. And so, going back to Wagner, his idea was very simple. I'm going to take the brain of geniuses, I'm going to take the brain of insane people, of criminal and normal people, and I'm going to compare them and find what makes a genius. And hence, he asked Gauss's family to donate the brain, and he received the brain. And here is a beautiful drawing that Wagner made. So what do we know about Gauss's brain? He measures its weight, measures its area. We know it weighs about 1,492 grams. Okay, is that big? Is that small? Well, you have to have an idea of the population before you can make any statement. So let's study just that problem with modern data. Here is data from the Dunedin study. I'll tell you a little bit more about the Dunedin study in a moment. So it's a study here, 435 people, all 45-year-old male, and you can put them in an MRI scan and easily get out of that the volume. And then you can bin that in to make a so-called histogram, where you put the number of brain you have in, within a given interval of volume. And then you can show that a very good model for this type of data is nothing but the Gaussian. The Gaussian is this relatively simple function, also called the normal distribution or the bell curve. And it has two parameters only, which is the mean, where the maximum of the distribution is, and the standard deviation, sigma, which is the width of this Gaussian. Now, since we are in the Gresham College, I have to tell you that the name standard deviation was first introduced here in the Gresham, by the Gresham professor of geometry, Carl Pearson, in 1893. And the name histogram, normal distribution, also introduced by Karl Pearson. Okay, so this is a distribution of volume, but we really have the weight. And the weight comes from the autopsy of gauzes. So here is another data set that I use. And the data is directly out of weight, and it's taken from more than 2,000 autopsy reports done in the 70s, before the invention of MRI scan. And it's very closely related. The mean is 1,390 grams, and with a standard deviation of 120. So the different region that you see is what we know from the Gaussian, is that within the one standard deviation, about 68% of the population is, or the distribution, and then 95, and then 99.7, and so on. So we all want to know, where does Gauss sit on the Gaussian, of course? Well, here is Gauss. It's not doing bad. His brain is about 80%, his brain is bigger than 80% of the population. But nothing like the 1 in a billion genius that his achievement attests. Okay? But we can look at other brain of mathematicians as long as we're here. We can look at Dirichlet. Dirichlet died in 1859 at age 54. He was the father of analytic number theory. Okay, big brain, good. That still works. How about Charles Babbage? Well, if you go and walk 10 minutes from here, you'll get to the Antiquarian Museum, and you can see the brain of Charles Babbage, if you're not too queasy. Lots of very nice pieces there. Also, a little bit bigger. He was the father, as you know, the grandfather of the idea of computer with Ada Lovelace. Helmholtz, the great German physicist, really the equivalent of Maxwell, also a little bit bigger. What about mentally disabled people, so-called idiot at the time? That was I put that in quote because that was an actual term used all the way to the middle of the 20th century. Well, that still works. But here where things get a little bit more difficult, what about one of the greatest minds of the 20th century, Einstein? Doesn't look too good, right? What about very, very big brain? Well, it doesn't look good either. There are pathology associated with very big brain. Okay, so we have a problem here. And as they gather all these different brain, not only in Germany, but also in Paris, where they had the Society of Mutual Autopsy, in the US, where they had the Anthropomorphic Society, and so on, they realized that there was really no ordering. At the end of the 19th century, Burt Green Wilder, an American anatomist, assembled a collection of 600 brains, and he divided in brains of educated and orderly persons and brain of unknown, insane, or criminal people. And so there was no relationship between the achievement and the size of the brain. Extremely talented people do not have, in any sense, extremely large brain. Okay. So that's a little bit a negative result, but interesting nevertheless. But we can now look at a slightly different question. Here we've identified different brain and see where they sit and all that. What if we take a big population of brain and try to find better measurement for both size and some sort of intelligence? And I have to tell you about the first attempt in this direction, which was made by Karl Pearson. As part of his lecture, he studied about 1,000 brain. And in 1906, he wrote an article in Biometrica, the journal he founded, on that problem. Now, Karl Pearson was the professor of geometry, and despite the respect I have for him, I'm in a very difficult position here, because he was also the founder of eugenics and a promoter of his social implication policies his entire life, and has the most abhorrent view related to races and other topics. Nevertheless, his contributions are undeniable, immense in statistics. He developed Pearson correlation coefficient, the chi-square test, the principal component analysis. The very language that we use for statistics all over the world is mostly due to Pearson. Immense. And when you look at his work, and we see his scientific rigor is perfect. So with that caveat in mind, let me tell you about his work. He looked at 1,000 Cambridge students, that's interesting, and 5,000 school children. And what did he do? Well, he looked at the size of the skull, because that's the only thing you can do. You can't look at the brain at the time. So he looked at multiple parameters, not only the size, the head width between the two ears, and the head length between the glabella and the occiput, and other index, like eye color, like hair color, curliness, everything he could think of, measured, and put that in table. He loved data, he loved statistics. He was living by data. Okay, so he had all this data about size, and some of them were collected as part of his job as Gresham Professor of Geometry. So what about intelligence? Well, he developed a system called Menteses, which is mostly the equivalent of IQ. And Menteses, he said, I'm going to put the mean at 0, and I'm going to have a standard deviation sigma to be exactly 100. And I'm going to put different people in different categories. For instance, Cambridge student with a first-class degree would be at least 2 standard deviations away, maybe not a genius. Genius is like 1 over 1,000, but definitely specially able. And that was on the good side. On the bad side, you'll have more interesting categories like very dull or imbecile or even worse, idiots. So in psychiatry and psychology in the beginning of the 20th century, you had idiot, imbecile, and they invented another term for people above that, which are morons. And that was the official category. The word morons was invented as a characterization of intellectual abilities. Okay, so he asked the teacher to rank the students and say in which category they would be put. So he had the number. Now, let's assume for a minute that we have some form of data that are both size and intelligence. What do we do with that? Well, let's assume that we have 5 of these points. Doesn't matter which one, we can take the one from Pearson, or we can take the one we'll use later. So for each one, we know some number for intelligence and some number for size, I and S, I1, S1 to I5, S5. The idea to see if there is any relation between the two is to try to find a line through this set of points. And we can think of this line, so this line would be AS plus B, where A is the slope and B is the intercept. And then we can think about moving this line everywhere until we find the line that goes the best through the cloud of points. So how do we do that? Well, we look at the vertical distance between any line and the point, call it D, D1, D2, D3, D4, D5, and we look at the square sum of all of these. And they all depend on A and B, because as I change my line, these numbers change also. So they're function of A and B. And I can find A and B that minimize D. And this is the so-called least square method that was both invented by Legendre and Gauss around 1809. And it leads to the so-called line of best fit in that data. Okay? So that was already well understood by Gauss. But Pearson went one step further. He said, okay, now that I have a line, how good a fit is it? Is it a line? Is the data very close to that line or far away? I need an estimate of that. And he came up with different coefficients, and the most well-known one is the Pearson correlation coefficient, usually called R. And R is between -1 and 1. If R equals 1, all the points are very precisely and exactly on a line. So that's the best possible case. It doesn't happen in statistics, always noise and errors and all that. So typically, you might have something like that, 0.8. You can still see with your eyes a line going through that. Or 0.4, still okay. All the way down to 0, where there is no relation. So 0 is bad. That means there is really no correlation between the two variables. It can be negative, because the line can go the other way. So for instance, if you look at a brain volume as a function of age, we know that brain volume decrease more or less linearly past the age of 30 or 40, all the way to 90 and so on. And in the same way, we have different numbers all the way to -1. So this is Pearson correlation coefficient. To this day is the simplest and most important number that you can associate with how good your fit is to a given set of data. Still used every day all over the world. Okay, so let's look at some of the results that he had, where here is a plot of size versus intelligence from his paper, and this is the intelligence of Cambridge graduate. And you can see the first class honor, second class, third class, or pass. Okay, and he looks at first around head length, and here is the line of best fit. It's a very good line. And here is the same study for head width. And he sees essentially that there is no correlation. It's essentially flat. When one varies, the other one doesn't vary. So he can't really say anything. He tried that with plenty of other variables, plenty of things, and concluded that the correlation is so small that they are, in every case, of no use for prediction. And if you wish to take anthropometric character into account, you might as well take hair and eye color, or curliness, he says. That's good. And so he concludes that the result of his inquiry convinced him there is no relationship between physical and psychical character in man. Of course, we're not going to go into the detail of everything that goes wrong, right? Cambridge student, why do you expect that at first? Let's not even go there. Or the bias of a teacher with respect to some of the students and so on, or even the measure of the skull as a measure of brain size. And we know from phrenology that the skull is not very good to say something meaningful about the brain. So what do we do? So we have to do the work again. Now, again, we need two things, size and intelligence. Now, size was very fortunate. Starting in the 80s, the magnetic resonance imaging method, MRI scanning, came into the medical world. And by now, there are probably at least 100 million brain scans that are made every year. So brain volume, you can push a button and you'll get the brain volume for this. No problem to get that kind of data. Now, the real question is, what do we say about intelligence? And that's, of course, a very difficult topic because it touches us directly. There are a lot of different opinions, very controversial, abuse, and so on. But let's agree that we know that there are different cognitive abilities. You take chess players and so on. If you take mathematics, it's a good example. I know painfully from my daily interaction with my colleagues that some are very smart and smarter than me. But intelligence, in general, measures an agent's ability to achieve goal in a wide range of environments. That's a very rough definition. There are hundreds of definitions, and philosophers can argue about this. I just want a number that's mostly representative of average cognitive ability. And so comes the IQ, the intellectual quotient. The old idea of IQ, the early one, proposed by Binet, who was interested in child development and identifying children which have the same mental age for education purpose, is to divide the mental age by the biological age and multiply by 100. So if you have a child that is age 10 and has a mental age 14, then she would have an IQ of 140. Okay? But it turns out that this definition is not very good. It's very hard to have a good concept of what mental age is. It's completely useless for adults because there is no reason to think that between age of 30 and 40, your actual cognitive ability would change and you would divide by a larger number. So without doing anything, your IQ would go down just because you age. So it didn't work. So the modern idea is, again, to use a good old Gaussian, and whatever set of numbers you have coming out of tests, we'll talk about tests, you would just put the average to 100 and standard deviation to 15. It's very easy. You do a translation, multiplication. You can do that in an Excel spreadsheet, no problem at all. And then it's very clear that, for instance, IQ of more than 130 would only be reserved for 2.5% of the population. Congratulations, you can go to Mensa if you are willing to pay the 60 quid fee every year and you think you might enjoy the company there. So, intelligence and IQ is, as I said, very controversial. Why? Well, one of the early arguments from Edwin Boring, the historian of psychology in 1920s, he says, intelligence is what the test tests. That's the definition of intelligence. It's a very circular argument, because what we really want is compare intelligence to something else, right? So the question is really reliability. And there you have a whole spectrum of views, all the way to the extremely skeptical one by Stephen Jay Gould, the famous American biologist, who wrote an entire book about it. He's a beautiful writer, The Mismeasure of Man, who says intelligence cannot be distilled into a single number. And he has an entire argument for why IQ tests are bad. All the way down to modern view of psychology or intelligence field, which has shown that the measurement of IQ tests is actually, surprise, a very good predictor of both grade at school, performance at work, and other aspects of life. And is also very stable. It turns out that it's one of the most reliable measures across age. That means the ranking of different in a given population will be stable over time. Maybe the IQ would change, but if somebody is way above, they would, on average, would stay in the same category. So IQ play a role. However, we also know that there are many misuse and abuse of these ideas going back 100 years and up to this day. Let me give you an example. For instance, Daily Mail to 2022, you might read the headline, a British boy beats Einstein and Hawking with 162 IQ, and he's going to join Mensa. Great. 2 years later, Daily Mail, the schoolboy 12 is accepted into Mensa. Great. With the same IQ as Albert Einstein and Stephen Hawking. Great. He's expecting to find friends there, supposedly. So, of course, you're going to tell me, well, what do you expect from the Daily Mail, right? But look at the venerable Guardian a few months ago, who had a title, the Devon schoolboy, another one, it's an epidemic here, joined Mensa with higher IQ score than Einstein and Hawking. Okay, that's great. I mean, I'm sure these kids are great. I don't know all they'll do at Mensa. What I do know for a fact is the following. There is no evidence whatsoever that Einstein or Hawking ever took an IQ test. What I do know is what Hawking had to say about IQ tests, is that people who boast about their IQs are losers, which I think we can all agree. So there are many different tests. The one that is mostly used is the Wechsler Adult Intelligence Scale, replaced the Stanford Binet in many cases, to introduce aspects that are not so much related to language. It's a series of 10 to 15 tests. It has many different ones, and here is an example of the kind of test that you can see. This is a matrix test, and what you see is, as you can guess, trying to find the missing piece in that matrix puzzle. So I thought maybe we use a collective intelligence to try to figure this one out. Okay, I see a diamond with a little black triangle on the left. The next one is a diamond with a little triangle on the right. And the third column is a diamond, well, with the two triangles together. It's like they add each other. Do you see that? So the next line, is doing the same thing. And the third line also. So my guess, but I had plenty of time to think about it, is that it's number 8 in the puzzle. And I have to say it's my guess because when I do this puzzle, I find very good logical reason to have one answer to find out that the people who made the test had another explanation for it. Okay, that being said, you can do this test and all that. Okay, so now we know that we can use these, they're very normalized, very well established and all that, they're standard. And we know we can get brain data on volume. And there's been probably dozens of studies trying to relate size or volume since the development of MRI to some form of intelligence. And the literature is very confusing, meta-analysis, looking at large data set and so on. And the problem with IQ is that it's very technical and it can go very wrong also. So I wanted to find a very clean, pristine data set on which I could do the analysis without relying on other scientists. And that brings us back to the Dunedin study. So Dunedin study is a fascinating study. Dunedin, New Zealand, people at the university in New Zealand decided to start a very long study. So maybe you remember this, one of the greatest documentaries of all time, 7 Up, 14 Up, 21 Up, and all that by Michael Apted, who look at the same kids evolving to the age. Where the Dunedin study is the scientific equivalent of that. They look at a population of 1,000 children born between April 1st, 1972, up to a year later. And they follow that population by looking at all vital signs and different signs, intelligence tests, blood tests, and all that through the years, and did a remarkable study, a longitudinal study of this population. It's a very homogeneous population. The tests are exactly the same given to all, so we have the data is very clean. And I saw one of their papers. They don't discuss this problem, but I contacted them. I says, I want to share the data with the good folks at Gresham College. Can you give it to me? And to my surprise, I said, sure, of course, if it's Gresham. And so I got the data, and here is the data plotted. So what you see is the IQ done by this Wechsler adult intelligence scale versus the brain volume obtained by MRI scan. And right away, you see that there's two populations, one in red and one in blue. So you might already guess that they're quite different, and they're quite different because the red are women and the blue are men. And you can see right away that on average, men have bigger brain, and that's just a direct result of the fact that men are taller than women on average, and there is a very strong correlation between size and brain volume. Nothing strange that. But we'll come back to that difference in a minute. So what you also see is that if I look at one given volume, there is huge spread in the data, right? So if I take the one close to the average, I can find people that would be welcome at Mensa and other people that would be not so welcome at Mensa, I would say. Very large spread, which goes against, again, to say that you cannot really, for two individuals in a population, you cannot make any statement. We're looking at a whole population level, right? It's very different. But now we can apply Gauss's method, line of best fit, to that data, and Pearson's and obtain the Pearson correlation coefficient. All the details are actually in the text that you can find on the website with the computation. And you find a line like that. It has a positive slope, so it says that IQ increase with brain volume through this element, with a rather modest correlation coefficient of 0.2. And if you look at other study, essentially it varied between 0.17 to a study that had more than 18,000 people, or using the UK Biobank, that leaves close to 0.28. What that number tells you is important. The square of R square, so the square of 0.2 is 0.04, so that's 4%. It tells you how much of the variation in brain volume can explain the variation in intelligence. So it tells you that the variation of intelligence can be explained between, the change in brain volume can explain between 4 to, let's say, 9% of the change observed in brain volume. So we have an interesting conclusion here, is that, yes, there is, at the population level, an effect of brain volume on intelligence. You really have to wrap your head around making sure that you understand that it's very different than boasting that you have a higher IQ because you have a bigger head. Right? It's a very different statement. Okay, so not a great effect, but clearly if we start comparing ourselves to animals, the difference should be clear. We all know that we have bigger brain than animals. Come on. Okay? So let's study that, see if we can see an effect there. Here is a drawing of a human brain. And it's big, it's 1.5 kilos, but it's not that big. Not when you compare it with an African elephant, which is 5 kilos. So we do not have the biggest brain in the animal kingdom. Not by far. If you go again to the entire collection, after you're done looking at Charles Babbage, you can admire the brain of a whale, which can go up to 9 kilograms, much bigger brain. Of course, you're going to tell me, I know what people say, well, wait a second. Elephants and whales are much bigger, and that you have to take that into account. Okay, so let's take that into account, and let's take a human, an African elephant, and indeed, they are much smaller in proportion to the size, as Aristotle said. Okay? In this case, in humans, brain makes 2% of our weight, where elephant only 0.1%. It's also very costly to have this 2% because it uses 20% of energy that we consume. It's another problem related to energy. Okay, so maybe we found something that distinguishes us. In proportion to our size, we are the best. Well, that's the problem with biology. It's full of exceptions. So let's look at the elephant nose fish. It was a very stressful life as an electric fish in freshwater lake in Africa. Well, its nervous system makes 3%. Or what about the short-tailed shrew? 7%. Well, we can only assume that we agree here that we're probably more cognitively able than the shrew or the elephant nosefish. Or we're the only animals who worry about this detail, let's just say. But we know in biology that when we compare the different weight of organs, usually the kind of scaling, the way things change, are not just in proportion. This is not what you expect in a linear scaling. There are plenty of examples in the animal world that are not just proportion. And that's the difference between linear and nonlinear scaling. When you have a linear scaling, you have a bunch of points, and you know that a line would be a good fit for this type of point. And we know that this line, now we've learned we can apply this square method and line of best fit, and we can find the slope, and we can find the intercept, and we're good. But most of the data in biology, when you look at weights against the whole weight, this theory I call allometry from Huxley, look very different. They look much more like a nonlinear function, like a parabola. And what you see is that a line, that's not a good fit. You can see with your naked eye that a line is not a good fit. You don't need to do any stats to find that out. What you really would like is to find this function, which is a much better fit for the data. Now, it's a power. It is called power laws. And the problem is to find them. It's that, oof, that's a tough problem. Now I have to redo everything. But wait, there is a wonderful trick here at work. If you start with y equals bx to the a, you can apply the logarithm on both sides. You haven't done anything. All these quantities are positive, no problem. And you can remember that the logarithm of a product is the sum of the logarithm. So you can simplify the right-hand side. Again, all the details are in the text. And what you find is that log y is now a linear function of log x plus a constant term, which is exactly the same form as before. So all you need to do is, instead of plotting the data y against x, is to plot log of y against log of x, and now the data that was in this nonlinear law stand on a line. And the idea then is to look at a big population of animals, and then us humans will find a place that, oh, we are outside the law. That means that we've beaten nature and evolution and have developed special abilities. Okay, the important in these power laws is the power. That's really the important fact. You can have a positive power larger than 1 or negative or less than 1. And when you transform that, here I take the logarithm, or I plot things on logarithmic scale, which is the same. So these nonlinear law transform into lines. The important is the exponent. If the exponent is bigger than 1, you are faster than linear. You go faster than what you expect. And when exponent is less than 1, you're slower than linear. So when you double in size, in weight, you're not going to double in size for that particular organ. If you talk about the brain, B, if A is less than 1, when the animal double in size, or if I compare two animals which are twice the size, the brain is not going to. So now we can use this ID, and I found a very nice data set of all animal brain weight and against the body weight. It's a wonderful time where you can find all this data these days and manipulate that yourself very easily. And here is the plot. And you see that for many decades, going from the shrew, tiny 1 gram, all the way to thousands of kilograms for the sperm whales, they more or less, you can see, fit on a line. There's a whole cloud that is well approximated by a line. But since I have a log scale, that means brain weight scale to the full weight, W, as power A, where A turns out to be extremely close to 3/4. And that's for a set of 1,552 mammals. So when biologists, evolutionary biologists typically, or comparative zoologists, look at these and they find an exponent like that, typically they would try to find a reason for it. It says, ooh, 3/4, that's interesting. There are other laws that are known with 3/4. There's Kepler's law, which is more than 100 years old, that says that the metabolic rate as a function of the body weight also scale like 3/4 power. So maybe the size of the brain is related to the metabolic demand. But when you start looking at this argument, it quickly falls apart. And the basic fact is that there is a scaling, the data really strongly suggest it, but we don't really know why. We don't have an overall explanation. And you can ask, where do we sit? Clearly, we should be outside, right? These are just animals, come on. Well, we're just there in the clouds. There's nothing special in terms of scaling. We do not distinguish ourselves by having a particular big brain weight, let's say, compared to dolphins, for instance, if you look at the scaling. And if you look at different subgroup of animal, for instance, dolphin and whales, or carnivorous, or primate, they all have different slope. And what it tells you is very interesting. It tells you that these groups have essentially had some trade-off through evolution of increasing brain size or increasing body size, in the case of whale, in order to accomplish or function better in the environment. And these trade-offs are different for different groups of animals. They've made different deals with nature in order to adapt themselves or be selected to evolution in their environment. And you can go much closer into all these ideas. And one of the persons who look at that is a scientist of the day, is Professor Susana Herculano-Usel. So let me tell you a little bit about her. She's a Brazilian neuroscientist who had a PhD from Paris in 1999. Then she went to work at Max Planck Institute after that. Then she went back to Rio de Janeiro, where she was professor for a while until she moved in 2006 to Vanderbilt University in Tennessee. She's been involved in science communication. She has an excellent TED Talk, for instance. And she has made important contribution. She challenged many of the neuromyths, especially regarding the number of neurons in the brain, and also the exceptionalism of human brains, the kind of scaling that we saw, that brains are not that different when you look at this scaling law. There must be something else. And she has a wonderful book on the topic called The Human Advantage that I recommend. Now, let me tell you, one of our ideas is to say, well, we shouldn't really look at brain volume, because what we really use is neurons, not the full brain. That is, it can be different for different animals. So she looked in detail into neuron numbers. So what are neurons? Neurons are the most important cell for cognitive process. They're electrically excitable, and they communicate with each other and essentially support all sensory, motor, cognitive function in the brain. It's really what the basis of all processing, and we'll have plenty of discussion about neurons. The problem now is just, how do we count neurons in the brain? Well, Susana Herculano-Usel, Professor Herculano-Usel, came up with this method called the isotropic fractionator, very nice name. And here is the idea. This is from a paper from 2023 where they look at two populations, one with high education and one with low education, and they compare the number of neurons in each of them. And the process is that you start dissecting in little cube and all that, and essentially the isotropic fractionator is a blender where you blend the whole thing and make a soup of it, and then you tack the nucleus of the neurons with a particular chemical agent. And then you can do normal imaging and start counting that. They're classical methods. So the idea is beautiful. It's not that complicated on the chemistry, but of course to do it in actual brain is quite demanding. So how many neurons are in the human brain? Well, the estimates are very interesting. If you go back to 1895, the first estimate was 3 billion. Then in 1981, you have this rather strange estimate of 1 trillion. But more or less, it's settled around 1985 to the value 100 billion. Okay, so when you're a mathematician and you see the number 100, it seems very round to me. And that roundness means that, well, it's probably a very vague estimate, right? Otherwise, it'd be 100.1 plus or minus something or something like that. No, it's 100. This is the number you see in many textbooks, it is for at least 20 years or 30 years. That was the consensus, 100 billion. It's impossible, actually, to find the place where it started. Up to the point where the group of Hercule and Husserl came, and in 2009, they established that the brain has 86.1 plus or minus 8.1 billion. And that's one of the most cited papers in neuroscience, with over 3,000 citations. Now, when I see a number like that, I said, well, that's awfully precise. The other one was a little round, but this one is very precise. So I went back to the paper. You always have to go back to the paper. It's a very interesting paper, very important, in the Journal of Comparative Neurology. And what you learn from the paper is the data is on 4 male, and here's the number, n equals 4, from 79 to 95.4 billion. And indeed, if you take the sample mean, if I just compute the average, I get 86.1, and the standard deviation, 8.1, no problem. But now let's think a little bit about that. If I want to establish the average height of humans, I could take 4 people in this room and measure them and say, aha, I average them, and that's the number. But you would say, well, that's rather strange. Why it is 4 and not other 4? You might have a mistake, right? So clearly, if I take 1 or 2, that might not be enough. Or about 4? Well, of course, statisticians have been thinking about this problem for a long time. What do you do when the number of data points is very small? You're really limited by what you can actually say in statistics. In that case, there is a method for that, and you can show that the margin of error with 95% confidence interval is given between x plus and x minus. That's given by a nice little formula, where it's mu plus or minus t star times the standard error, which is sigma over the square root of the number of points. T star comes from the student distribution, the t distribution, also heavily studied by Pearson. And you can find the critical value for n equals 4, which is about 3.182. So the only thing you can say about this data set is not that the average for the population is 86.1, but that the average for the population is somewhere between 73 and 99. Very different statement, much weaker. But that's what we can say. Okay, not bad. But things get a little more complicated, as usual. There was another paper, also from Brazil, another excellent paper comparing a healthy brain with people with neurodegenerative disease. And it has 5 healthy brains of women. And in this case, you can do the same analysis, same playing with the same numbers, and you find that the mean number of neurons in female brain is between 62 billion and 73. So now we have a big gap somewhere between 62 and 99. Or we can say, just look at the data, and you can say that observation vary between 62 and 94. That's the best we can say. So we do not quite know how many neurons the human brain has with any kind of statistical significance. which is startling because there is nothing that's more studied in science than the human brain, for which you know the more minute details, except the number of neurons. But that's not important for us, because even this estimate is good enough for comparing us, humans, with animals. And she made an very interesting point. She started looking at rodent and primate, and she said, look, the capybara with 76-gram brain has only 1,600 million neurons, whereas the tiny capuchin monkey has a smaller brain, but more than twice the number of neurons. So brain weight or brain volume really does not tell you that much, because it's really the number of neurons that matters. And you can look now and compare between different rodents and primates, and you can do the same scaling game, where you look at the body mass, or the number of neurons, against the body mass. And what you realize is that different groups of animal, primate versus rodents, sit on completely different scaling, different lines. And that's what really distinguishes. Again, different groups of animals have evolved differently with different constraints that lead to different basic choice. It's not choice, of course, but different evolution through time of the number of neurons. And that's the starting point for all type of comparative anatomy. Of course, where do we sit? Well, we're still there on the law. Nothing special. And in the world of Herculano Husserl, she said, humans are nothing but a scalar primate. We just sit on that line. There is nothing particular at that level that distinguishes, which leads to a very interesting question. Why is there such a gap, a qualitative gap in cognitive ability, if we share essentially the same type of scaling? And it's the same question that you get nowadays in artificial intelligence and large language model, where the number or the performance or the learning time also scale as power laws. And when you also realize that when you reach a certain size, all of a sudden you have a qualitative jump in abilities, where these programs can all of a sudden do a lot of tasks differently. Okay, so there are a lot of very good ideas there. So, what did we learn? Well, when we look at humans, we can turn to Charles Darwin, who had always a piece of wisdom. It's very clear that you cannot compare two people. No one supposed that the intellect of any two men can be accurately gauged by the cubic content of their skulls. However, at a population level, there is still an effect that can be observed. And let me come back to that difference between men and women. Women are, on average, 11% smaller brain than men. So statistically, their IQ should be different if they were really part of the same group. However, when you look at the IQ, they're both exactly 100. And that tells you also something interesting, is the way women use their brain, at least during IQ tests, is different than the way men use. In a way, women use their brain more efficiently to make up for that difference in volume. So we have two populations, and despite the fact that they have different brain volume, there is no statistical difference between their IQ score. Now, what about animals, where there is, again, nothing that specially distinguishes in the animal kingdom, but, as also Darwin says, what is really remarkable is what can be accomplished by a small brain. If you compare us with reptiles and birds, crocodile is 700 kilograms, has a tiny brain of 10 to 20 grams, but is still able to accomplish very sophisticated behavior that serves them very well over a very long period. And Darwin says, the brain of an ant is one of the most marvelous atoms of matter in the world, perhaps more so than the brain of a man. Okay. So let me go back to Gauss. Wagner realized that there was a problem. His son took over, realized there was a problem. There was nothing special about the volume that was not going anywhere. Then he realized, well, maybe there is something different looking at the brain. He says, the cerebrum is remarkable for the great complexity of convolution. So if it's not brain size, maybe it's in the complexity of the geometry of the brain. And that's what we'll be talking about in the next lecture. Thank you.